Oh, and then it's okay. Just give people a chance to connect. Okay. Well, maybe we can get started. I can introduce you, Paulo.
Sure.
So today we're very fortunate to have Paulo Bedaque come give a seminar on Zoom. Paulo is at the University of Maryland, and he's going to tell us about quantum computers, gauge theories, and fuzzy stuff, qubitization. So we'll see.
Yeah.
Awesome. Go for it, Paulo.
Yeah. So thanks for having me.
Okay. Thanks.
So I know I'm not supposed to use made-up words like qubitization in a title. I had an alternative title that I flashed here, but then my colleague said none, and I go back to the original one. All right. This is based on work done with a bunch of people. I think I listed them all here, all young people that you should know. Anyway, the motivation is just very simple. I'm interested in doing numerics in quantum field theory. And the way this is usually done is that you use classical computers based on, classical logical gates, the usual way, right? And the idea here is that you're not going to do this. Someone else is going to build a quantum computer that works on slightly different principles. So instead of having bits that you manipulate with logical gates, you're going to have qubits that you manipulate with quantum gates. And there's a set of gates that probably every future machine will implement in hardware. There are single qubits, and some of them are 2 qubits, and sometimes more complicated things. And the novelty here is that, so there's a restriction, right? First is that the computer obeys the laws of quantum mechanics. So whatever evolution you're going to do here is going to be a linear, in fact, it's going to be a unitary evolution at every step. Now, the way we use computers, classical computers, to do physics is that we get those computers that were designed to play video games, and you use the primitive functions that they have embedded in them, like multiplying numbers, right? And we do whatever we want with our algorithms. The problem is that in quantum computers, there is proof that you can do a few things much faster than we could with a classical computer. Famously factory numbers and a few other things. None of those things have an immediate application in physics. So in particular, there's no reason to expect that a quantum computer is going to multiply numbers faster. So the question is, how would you use these machines to do physics? Okay? And it seems like a very complicated problem because quantum algorithms that have an advantage over classical ones are just rare, and they're complicated, and they don't do things you want them to do. On top of this, there is the question of why. Right? So a standard answer people give is the following. Systems, field theory, systems with a volume V, they typically have a Hilbert space dimension that's exponential on the volume, and manipulating matrices like the Hamiltonian, inverting, diagonalizing, they have a cost that's the cube of that. So there's an exponential cost in the volume to do physics in the naive way with classical computers. Okay? There's an alternative, of course, that's Monte Carlo. Monte Carlo doesn't cost exponential amounts of time. It's roughly the volume or a little more than that. However, as it's well known, Monte Carlo fails a bunch of things. Real-time observables, problems with finite chemical potentials, et cetera. It happens to be from the corner, those problems are very popular and important in the corner of physics I'm from, that's nuclear theory. So for us, it's an obvious impediment that really is, I build a career around trying to solve those problems in different ways, right? Now, the big advantage in quantum physics is that there is a very natural algorithm or a class of algorithms just to do quantum physics in quantum computers. That's basically to simulate the quantum system using the quantum degrees of freedom of your computer. So imagine you have some system, you prepare your memory, your register, your quantum register, in some way that encodes the initial wave function. Then you break up the time evolution, the real-time evolution, into little pieces using the Trotter formula. And each one of those you manage to implement in terms of some quantum gates. And the advantage of doing this in little steps is because to compute this exponential for small delta t may be a doable thing. But the full-time evolution is equivalent to solving the problem exactly, so it's not doable. Okay? But you do this, and then you keep applying that to the register, and then at some point, you make a measurement. And that's how you solve your physics problem. And of course, in principle, you can do measure any observable that way, because that's how experimentalists do, right? They prepare a system, they let it evolve, and then they measure stuff. So in principle, you can use this algorithm to do anything you want in physics. Right? The question is, do you have an advantage here over doing the same thing with the classical computers? Well, definitely, right? As I said, manipulating this matrix, this Hamiltonian here, it has an exponential cost on the volume. On the other hand, this algorithm here, it's basically the cost is proportional to the number of gates. And if every time step doesn't have a huge number of gates, the cost is going to be just proportional to the time. Also, the cost in memory. I don't need an exponential number of qubits to describe my system. In other words, the number of qubits is going to be proportional to the volume, as opposed to the case of bits that have to be proportional to the exponential of the volume. So it seems like, obviously quantum computers are very good to do quantum physics, but there's a lot of details left, right? So it's not the only one paradigm, but that's the main paradigm that people think about using quantum computers in physics, is to follow those steps. So basically, your actual physical system has a Hilbert space, and you have to map it somehow into the qubits of your computer. Then you have to have a technique to prepare the initial state, whatever initial state you want. Then you encode your Hamiltonian, the Hamiltonian of the actual physical system, into quantum gates. And then you evolve, you apply the Hamiltonian or the unitary evolution over and over, and measure wherever observable you want. Each one of those steps deserves not only a paper, but a book. And people work in all those different things. So when I say that I'm going to explain how to do physics with quantum computers, I'm going to just concentrate in one aspect of this. And it's the first one. You have a physical system. I want to encode this into a finite number of qubits. And it turns out that this is not a trivial problem. And the reason for this is the following. Well, in field theory, Hilbert space has infinite dimensions. I mean, even harmonic oscillators have infinite dimensions, right? So there are some steps of reducing the Hilbert space to a finite dimensional one that are very standard. So discretize space and maybe time. That's what we do in lattice. You put in a finite volume, and we do this on the lattice all the time. For fermionic theories, that's enough. But for bosonic theories, you have to face the fact that even if your theory has only one site in space, your Hilbert space is already infinite dimensional. In other words, you can put as many bosons as you want in one site. So you need some kind of truncation on the number of bosons or on the field space that was not required in lattice theory up to now. It's this process here of going from the infinite dimensional Hilbert space to the finite one that I call qubitization. I think Shailesh used this expression before me. I liked it. I use it now. Okay. Points 1 and 2, discretizing space-time and making a finite volume, are very well known from just lattice gauge theory. So I'm not going to dwell too much on it. So making this space to be a lattice, it's the usual story, right? You discretize the space, but you want to take the continuum limit. But you want to take the continuum limit in such a way that your objects, say you're describing a duck here, right? They keep the same physical dimensions as the lattice shrinks. So in lattice units, the duck is going to grow. And that means that in the continuum limit, you're going to be interested in critical theories. So you're going to have to tune your couplings in such a way that correlation lengths and all the other length scales in the theory approach infinity in lattice units. Anyway, this is complicated but well understood from lattice calculations. And the same thing with finite volume. You do a calculation of finite volume, your whatever observables, they get deformed. The kind of deformations that you get are well understood and sometimes are even used to extract physics. So again, I'm not going to spend too much time talking about this. It's the third one that's somewhat unusual. It's the fact for bosonic theories, I have to somehow discretize the field space or the occupation number or do some kind of thing. So the local Hilbert space of the theory is finite dimensional. Okay? So here's just an example that you're going to study later. If you have a field that takes values on a sphere, one possible solution to this problem is to make the field takes values only on the vertices of a Platonic solid, for example. Right? Now, it turns out that because this is new, there's a lot of issues to consider here. It's way more subtle than you might think. And there are things I know, there are things that I don't know. It turns out that there is one model, namely the sigma model, the O3 sigma model, nonlinear sigma model in 2 dimensions, that I think we understand most of it. So I'm going to use this example to explain a bunch of things and ideas and failures and successes. I will come back to gauge theories, and I'm going to draw parallels there. Okay, so I know you guys are interested in gauge theories. Nobody cares about the sigma model, but there is a reason why I'm doing this. Trust me, it's better to understand this on a situation that's completely under control. So there you go. The nonlinear sigma model is a well-known model, right? It's one space, one time. You have fields that take values on a unit sphere. That's what makes it nonlinear. It has an O3 symmetry, rotation symmetry. It's just O3 of the rotation in the internal space, right? And this model is well known. It's been studied for half a century, and in fact, is exactly solvable. What do I need to know about this model? Okay, so first, it's asymptotically free. So if you look at the length scales of this theory, there's going to be a certain mass scale, call it lambda. That's the analog of lambda QCD. Right? So the masses of the particles are going to be around there, and everything that's dimension full is going to be, around that scale. Momentum energy scales that are below that, I'm going to call infrared. Energy scales that are above that, I'm going to call ultraviolet. But if I study this on a lattice, as we're going to have to do, there's going to be a regulator. That's the lattice spacing. So the scale of the lattice spacing, I'm going to call the cutoff. I'm not going to call this ultraviolet. I'm going to call the cutoff scale. Just to emphasize the fact that cutoff, it's lattice dependent, it's a lattice artifact, it's not universal, and I don't care about what happens there. That's very confusing because every time I talk about this, I say ultraviolet and people think about the cutoff scale and confusion ensues, right? The other things you need to know about the model is that it's solvable. The spectrum has a triplet of particles, of massive particles. So the physics is not the physics of Goldstone modes. It's different. And in fact, phase shifts of the interaction of those particles is well known, and it's identical to a particles interacts as a delta function. Okay, and there is essentially there's no inelastic scattering. It's one of those special integrable models, right? All right, so I know this model very well. I should be able to use it as a test ground for whatever idea I have. It will be useful for us to do quantum computation to think of this in the Hamiltonian language. So in the Hamiltonian language, there's going to be a wave function describing the state of the system that's a function of all those unit vectors. Those are like the coordinates. And of course, the space of those functions is infinite dimensional. Even if I had one side, it would be infinite dimensional. There is a positional operator, basically, that gives me the components of the n at every site. And there is generators of the rotations, the O3 rotations. And it turns out that that action that I showed you before can be obtained from this Hamiltonian here. This looks like a kinetic term, like angular momentum square, and there is a nearest neighbor interaction. Okay. Let me just point it out that the position operators even at the same site with different components, they commute, just like X and Y commute in quantum mechanics. The generators of O3, of course, satisfy the O3 algebra, and they rotate this vector n the way vectors rotate. An obvious point. Okay. So one could use Hamiltonian language here and solve this theory. It's not done. I don't know anybody who does it, but one could. All right. Before we go any further, let me point out one little subtlety here. This Hamiltonian has two terms. It has this kinetic term, and there is this, that's why potential term. And I wrote the coefficients of them in a kind of funny way. I wrote as an overall constant and a coupling. And the rationale for this is the following. The eigenstates of this Hamiltonian are independent of this parameter eta. So the correlation lengths in space are independent of eta. It appears only on the energies, and it appears in a trivial way. It scales with that, or with eta. Right? So one way of solving this would be you tune the value of g until you get a wave function that has large correlation length compared to lattice spacing. At that point, you measure the correlation length, you measure the gap between the ground state and the first excited state, and you adjust eta, so the gap agrees with 1 over the correlation length. That's how you get a Lorentz invariant theory. So that's going to be a procedure we're going to do later on, okay? But anyway, that explains why I picked those constants this funny way. All right, the problem is that this is infinite dimensional. I cannot use this in a quantum computer. I have to truncate the theory somehow. So there's going to be 3 strategies. And of course, I'm going to argue that the first 2 are no good, and the third one is going to be good. First one, instead of a sphere, substitute the sphere by a discrete finite set of points. So the wave function that used to be a function on the sphere, that's an infinite dimensional space, is a function of a discrete set of points, so it's a finite dimensional Hilbert space. I'm just repeating myself here. Now, you'd like those points to somehow be well distributed over the sphere. Otherwise, you're not going to reproduce the correct model. In this particular case of the sphere, there are only 5 ways of doing this. You have to take those points to be the vertices of a Platonic solid. So you already see that there is a problem here. There are only 5. I can put 20 points around the sphere that are more or less well distributed. I can do more than that. I cannot do.
Would I ask a question? So when you solve it in the Hamiltonian way, can you numerically see that the energy gap is exponentially small, like of order e to the minus constant over g squared?
So I never solved the model as it's here because the infinite dimensional Hilbert space, I need some kind of truncation. And then I'm going to show you those results. Then you can maybe ask me again if it's not clear there. Okay.
Because the exponentially small numbers are hard, right, numerically?
Yes. Criticality is always hard. So that's going to be a problem one has to deal with. But that's a problem we deal with in the Monte Carlo lattice calculations too, right? There's some cost involved in, critical slowing down, et cetera. So I'm by no means saying that this is easy, okay? And I'm going to show you some examples as soon as I manage to have a finite dimensional Hilbert space where I actually do numerical calculations.
Okay, thank you.
I'm not advocating this is a good method by any means. I'm saying this is a good way of formulating for the day I have a quantum computer in my hands.
Yeah, I agree. It's a great method. Just want to know how much is known about how it works.
Anyway, I'll comment on a little more later. Okay? Anyway, there is a generic problem in substituting a continuous manifold by a set of points. People have done this, by the way, since the 80s, okay, for reasons that are completely different. And the basic idea is the following. You have an action that has a 1 over g squared in front, and you want to make g to be small to approach the continuum limit. It's an asymptotically free theory. For continuous phi, what happens is that the path integral is dominated by configurations that are very smooth, that have a very small action. And the smallest g, the smallest the action has to be. Higher actions are exponentially suppressed. Now, if our degrees of freedom were discrete, there is a configuration that has the minimum action. There's a gap between the configurations that have zero action and the next one. So when you make G very small, at some point, the system freezes out. All configurations are exponentially suppressed except one. The result of this is that you get a first order phase transition, and the theory has no continuum limit. And I'm gonna show a bunch of examples later in numerical calculations. That's exactly what happens, numerically. You can see that. So there are two issues. First, sometimes you cannot put an arbitrary number of points to approximate your manifold. And second, if you have a finite number of points, you cannot approach the continuum limit. There is no, these theories don't have a continuum limit.
Can I ask a stupid question?
Sure.
Why is there a cutoff on the number of points? Why can't you just not keep increasing them? Well, I mean,
Yeah, so that depends on the manifold here. Depends on the manifold here. So if it was a circle, there wouldn't be any problem. I can always substitute one symmetry by a ZN symmetry, make n very large. For a sphere, well, depends exactly what you demand about those points. But if you demand those points to form a regular polyhedron, in other words, that's well distributed over the sphere, well, the Greeks classify all possible ways of doing this. There are 5.
Why do you need to assume this? I mean,
well, because then it's unlikely that you're doing the O3 sigma model. For example, suppose you approximate the sphere by 300 points living along the equator.
Sure.
It's not going to work, right? So, that's a drastic example. What I'm trying to say is that if you try to make them equally spaced, so you have a subgroup of SO3, you're limited in what you can do. Okay. In the case that's interesting, that's SO3, this is much more sharply defined. Okay.
Excuse me, I have a question. In the early days of lattice gauge theory, I think some people at least, consider also irregular lattices.
You mean on field space? Yeah. So one can try to do that. I don't know. I don't have the full answer here, but I think it's a very dangerous road, because if you don't have the right symmetries, it's very unlikely you're going to end up with gauge theory, or at least the gauge theory you're after. Okay. But I don't have final answers to anything. Let me tell you something else that seems to be the most popular option here. In the case of the sphere, for example, instead of consider functions on the sphere, I can just expand the harmonic oscillator, the spherical harmonics, and then put a truncation on the largest value of the angular momentum. So that transforms the infinite Hilbert space of functions in a sphere into a finite dimensional one. It's also good because it seems to keep things spherically symmetric, and you don't want to give up on the O3 symmetry very theory. And that sounds like a good thing to do. So let me tell you a few more details. You'd have a Hamiltonian that's pretty much the same as before, except that what I mean by J squared, the generators of rotation. Well, here you go. It is the generators of rotation in usual sense. Anyway, you know how it acts on a particular spherical harmonics. One subtlety has to do with the position operator. Take the Z component of the vector, for example. When it hits a wave function, it produces things that are out of your Hilbert space. So NZ is just, what is it? Cosine of theta, right? So it's spherical harmonic with angular momentum 1. When it combines the angular momentum L, it produces L minus 1, L and L plus 1, some coefficients. Well, it turns out that the L plus 1, if L is your maximum value of L, this last term is not in your Hilbert space. So for this Hamiltonian here to act on the Hilbert space and have an image on the same Hilbert space, you need to truncate. And that's what's implicitly done. Okay. Is this a problem or not? We'll see. Okay. But in the case of L taking L max to be 1, you have a 4 to the n Hilbert space. N is the number of sites. Okay. So it's finite. Okay. It's exponentially large, but finite. Now, you can take this Hamiltonian and actually try to calculate things now. So you try to you find the ground state, find the first excited state, find the wave functions on a finite lattice, and you look how the correlation length or the mass, what I mean by mass is the inverse correlation length here, in lattice units as a function of the coupling. And what you find is that it goes down, the mass goes down and then stabilizes. So it doesn't look like taking G equal to 0, make the mass to be 0 in lattice units. In other words, you don't reach criticality. This model, that's a perfectly defined finite dimensional Hamiltonian, does not seem to have a continuum limit.
What is capital L? Can you remind me?
Yes. So I screw up because I changed the names. It's supposed to be L max.
Aha.
Okay. So it's the cutoff in field space.
Aha. Is there some reason you would think that without also scaling L max, you would reach a continuum limit? Because this doesn't sound
No,
like it
I
would
expect
work.
this to happen is exactly what's happened. So you're
Okay.
basically saying that the most popular approach is just obviously wrong, right? Well, people know this, but what people expect to do is the following. As you approach the continuum limit by making G small, at some point you can get correlation lengths too large. So you say, well, then I have to increase L. And then you go to L equal to 2. And then you go to a little larger correlation length. And then it doesn't work anymore. You go to L equal to 3. And there is some evidence that if you keep doing this, eventually you get to the critical point, because at that point you're going to be simulating essentially the original sigma model. There is no cutoff anymore. Okay, so yeah, that's exactly the expectation people have. You have to keep increasing L, and you say, well, you know, that's life, and that's all you can do. Why are you worried about this? So let me tell you first, because there are better things to do, but it's actually very problematic. So let me make the following argument. The same issue with approximating real numbers or discretizing real continuous fields happens in classical computers too. Classical computers are digital machines with a finite memory, right? So what you do there is that if you have some continuous number, you approximate by, say, 10 bits, usually more than that, but let's say 10 bits. And with 10 bits, you get a certain amount of precision. There's a certain quantization on the real numbers, right? Usually it's too small for us to care. We never think about this, but it is there. And there was a time in history where this actually mattered more. Now, suppose you're not happy with your precision. You need more precision for whatever reason. Well, what you do is to take more bits. So by adding a single bit to your register, you double the number of numbers that you can represent. So you double your precision. Now, what is the cost now of manipulating numbers that have 11 bits as opposed to 10 bits? Well, the overhead is tiny. It's just 10% more expensive. Right? The cost of multiplying numbers of this size is proportional to the number of bits. So the cost that you're going to have is going to increase slightly, but it's not much. In fact, in modern computers, you cannot even do that because there's a standard precision, and then you double the precision. What they mean by double precision is not doubling the precision, it's doubling the number of bits that grows the precision exponentially. Okay, basically, bits are cheap, and the manipulation of them is very cheap. Quantum computer is a similar story. You can approximate real numbers with a certain number of qubits, and if you need more precision, you add one more qubit. When you do this, you double the precision. The problem is that when you start to do the time evolution, and you have your pieces of the Hamiltonian have more bits, the evidence, it's not a theorem, but the evidence is that the cost grows exponentially, or probably faster, with the number of qubits. It's really drastic, and I can show you examples of this. So if you have a piece of the Hamiltonian that involves, say, 2 links, and there are 4 bits, there's a certain number of gates. If instead of 4 is 5, the number of gates grows enormously. And if it's 6, it grows even more. It's actually faster than exponential. The evidence is that's faster than exponential. So now think about taking the continuum limit, right? Yeah, you decrease G, you have to increase L. But when you increase L, you increase the number of qubits. And that increases exponentially the cost of my calculation. So I think that's not good. In other words, the quantum advantage that you had, that you could manipulate Hamiltonians of exponentially large size in polynomial time, it disappears because you have another exponential to bite your back. That suggests that you should try to do something else. Now, full disclosure, that's not how things happened to me. I just came up with that because that was the only thing I could do, and then I worked backwards, and it turns out I was very lucky. The obvious thing to me was something that it turned out to work. So the construction here, the third way, is the following. I'm not going to substitute the sphere by a set of points, but I'm going to regularize the sphere using a construction that's well known. I don't know who invented that, but I think it was invented several times. Anyway, you're substituting the sphere by what's called a fuzzy sphere. And I have no better picture of a fuzzy sphere than this. And the problem here is that a fuzzy sphere is not a set of points at all, okay? So following this philosophy of non-commutative geometry, you think of the space of functions on the original manifold. And in case of the sphere, I could expand in coordinates like this. It would be an infinite series, infinite Taylor series, and my coordinates would satisfy a certain constraint. You take that as an inspiration. And instead of generalizing the manifold as some set of points, you generalize the space of functions on that manifold. And the way you generalize is to say all the functions in my manifold, quotation marks, is going to be given by this. That formally looks like that, but of course it's a completely different object. It's not a function, in fact, it's a 2x2 matrix. The cute thing is that the constraint here is mapped to the constraints on the Pauli matrices. Now, this fits well the attempt of doing quantum mechanics of this system, because when you do quantum mechanics, you don't really care about having a configuration space. What you care is having functions on the configuration space, the wave function. So here, when I talk about the fuzzy O3 sigma model, I'm not going to have fields that take value on the sphere or in any other space. I'm going to have 2x2 matrices. That plays the role of my wave function. Okay. And this construction is called the fuzzy sphere. I know from attempts of regularizing main-brain theory back in the 80s, but it's all over. It's kind of an obvious idea that many people had it. Okay. Now, I wrote here Pauli matrices, but that's just one example. I could take here generators of O3 of a larger ERAP. Could be spin 1, 2, 34, etc. In that case, this wave function would be matrices of a larger size. And it can be shown that in the limit, you can map certain constructions of this wave function into regular constructions of the original sphere. So for example, the inner product of wave functions turns into this. The Laplacian on the sphere maps into something like this. And I'm dropping numerical constants here. Okay. So that's what I mean by a fuzzy sphere. Okay, it's not a sphere, it's not a set of points. It's just a way of thinking about the set of functions on the sphere. And that's substituted by a matrix with certain properties. And this wave function, the same way that this function transforms under rotations, this function is going to transform under rotations, and so on and so forth. Okay. One thing I want to point out is that in a regular sphere, if I have a function of the 3 coordinates of the unit vector, the operator corresponding to the components of a vector act on the wave function in the usual way. This is like X or Y on a particle on a plane, right? And of course, they commute by definition. Here, what's going to play the role of the operator of a coordinate of the field is going to be a Pauli matrix. And therefore, they don't commute. So in this sense, it is as if I was doing the usual quantum mechanics, but on a space, the configuration space, whose coordinates do not commute. From there on, it's kind of, it's downhill, right? It's easy. I will define the field theory on a lattice on a finite volume. So I regularize space, I regularize total volume and the field space to be this. This is the Laplacian. That's like kinetic energy. And there is a nearest neighbor interaction. At every site, this is the wave function is a 2x2 matrix. It's a 4-dimensional Hilbert space. So it's a 4 to the n. If I have n sites, the Hilbert space has dimension 4 to the n, right? But it's a finite matrix. That's what I'm trying to say. So it's a well-defined problem, and that you can diagonalize and find eigenfunctions and eigenvalues and so on and so forth, right? Now, one thing that's going to be important when you get to gauge theories is that the operator that implements rotations, they satisfy the O3 algebras, they should. They rotate the vector n as a vector, as they should. The only thing that's different from the regular sigma model is that the operators corresponding to the components of one vector, they do not commute. But that's never used in the construction. So for example, when I prove that this Hamiltonian has an O3 symmetry, I use these two conditions, but not the third one. So everything goes through, okay? So this is a perfectly legitimate O3 invariant, finite dimensional Hilbert space Hamiltonian. The question, of course, is whether this has anything to do with the sigma model I started, talking about. It's a different model, right? So how do we test that? So it turns out that Monte Carlo, I spent an enormous amount of time trying to do this, but it has a bad sign problem. You take this Hamiltonian here, you can find a path integral that gives me the partition function. And that path integral has a really bad sign problem. You can't do anything with it. However, there is this whole technology of tensor networks that works very well in one space dimension. So we learned that, we implemented that, and we went to town with it to solve this problem, right? And as I mentioned before, keep in mind that G square controls the wave function, and therefore the correlation, the spatial correlations. Eta changes only the energy. So what we do is we solve this with eta equal to 1. Tune G so the correlation length is large enough. Then you measure the gap and multiply the gap by eta. So the gap and the correlation length match each other. Eta is not 1, by the way. It's a different value from 1. It gets renormalized. So just to show that this is real, have a Hamiltonian, you can in fact break up the time evolution in pieces. That's the evolution given by the kinetic term, the evolution given by the x component of the two spins, and y and the z. And we can simulate in an actual computer, etc., etc. This is just for 3 sites, of course. If I had a quantum computer, I'll do this in 100 sites and solve the theory. What's the result that we get? So the main thing is this. The blue part I already showed is this angular momentum truncation, that when you make the coupling constant go to 0, so you approach the continuum limit, the correlation length actually does not diverge. But if you do this other model, the fuzzy model, it diverges really fast. In fact, this curve here is a fit to an exponential form because you expect this to depend exponentially on the coupling. So maybe that answers the question that I got before. Yeah, anyway, we're not too concerned about reproducing the correct exponential, but maybe that answers your question, okay?
Thank you.
It's a hard problem, I have to say. I mean, this tensor network, it's an MPS, variational bound state, variational ground state. It works for gapped states, but you're going for criticality, where the system became gapless. So you have to really push the computer quite a bit to do those things.
So the vertical axis is energy levels?
Yeah, it's the same as before. It's this mass in lattice units.
Okay.
All right. So this suggests that this model at least has a continuum limit. And this is fixing the rep. It's always a Pauli matrix. I'm not increasing the rep as I approach the continuum limit. So the number of degrees of freedom doesn't increase. The Hilbert space is still the same. Right? There's no extra cost in approaching the continuum limit. But then the question is, yes.
Sorry, what's the intuition behind not needing to increase your approximation, to increase the truncation level? That seems surprising.
I don't know the answer. I wish I did. So I don't have an analytic proof and a good understanding of why this happens. As I said, it was dumb luck that this fuzzy model works. Now I have conjectures and I have some ideas that I'm going to discuss in a second. Okay,
thank you.
But first, let me convince you that this model is not only has a continuum limit, it has the right continuum limit. This is the O3 sigma model. So this is a standard technique people do in critical phenomena, is to plot the scaling function. Scaling function is this object here. You look, the mass of a particle is going to depend on the volume. When the volume is very large, the mass becomes constant. When it's very small, it changes. So here we plotted the mass of the particle, or the gap, at two different volumes. And on the right, on the horizontal axis here, we have basically the correlation length divided by the volume. So let me break this out for you a little. Large volumes correspond to large L, large compared to the correlation length. Those appear on the left. Small volumes, meaning smaller than the correlation length, appear on the right. So this is UV, this is infrared. Okay. In the large volume limit, we imagine that the mass doesn't depend on the volume anymore. And in fact, this ratio goes to 1. At small volumes, what's going to happen is that for tiny volumes, imagine having a QCD, a volume that's a fraction of a Fermi, right? The states are going to be essentially massless. And the effect of the volume is just going to be the difference between having 0 momentum and the first allowed momentum in periodic boundary conditions, 2 pi over L. So when you double the volume, you pick a factor 2. That's the difference between 0 and 2 pi over L and 0 and 4 pi over L. So it approaches 2 here. The interesting thing is what happens in the middle. Now, what happens in the middle depends on the interactions of the theory. So for example, down here, a large but finite volume, one can show that the shifting mass of a particle on periodic boundary conditions is given as a function of the phase shifts of that particle, basically because the particle interacts with itself around the lattice. So this part of the curve essentially is a way of measuring the phase shifts of the theory. Here, wouldn't be the phase shift, would be some other quantity, but it depends on the interaction of the theory. Different theories would have a different scaling function. Okay? Anyway, so now we take our model. We take the fuzzy model and calculate that. And you get, depending on the value of your how many lattice sites you have, you get different curves. Now, I plot a lot of points here that are way off the curve. They correspond to situations where the number of points in the lattice is very small. So you're very far from the continuum. So the idea is this: you pick a value of the coupling and you find this curve. And you're going to follow the expected curve, for a while, and then it decouples when the number of sites is too small. Then you take a smaller G, and a larger lattice, and a smaller G, and you get a different curve. And you do this. Now, the beauty of doing this, not with Monte Carlo, but with tensor networks, is that you get 10 to minus 3 precision on those things. So you can possibly see the error bars here, but there are error bars here. And the agreement is fantastic with what's known from either Monte Carlo or even the Bethe-Ansatz calculation of this curve. Okay, so that's the evidence that our model reproduces the sigma model, not only in the infrared region, but also in the ultraviolet region. I have to point out that there was a different group that did this. They came up with the same model for completely different reasons after us, completely independently, and they did a similar calculation with a different numerical method that obtained points up here in the ultraviolet, but less points here in the infrared. So this was checked by 2 different groups using very different technologies. So I think this is solid. Now, there is a surprise here that I forgot to tell you. Notice that I put 2 signs here, plus or minus. If I was inspired simply by the original model, I would have a minus sign here. In other words, I would favor ferromagnetic interactions. That's what you get by simply discretizing a spatial derivative in the sigma model. If you use the ferromagnetic case, if you take the fuzzy model in the ferromagnetic case, Jesus. Here you go. If you take the minus sign here, you do not get this curve. You get a curve, there is a continuum limit, but the curve is close, but many sigma away from the correct answer. What gives the sigma model is not the ferromagnetic case, but it's the anti-ferromagnetic case. And I think I sort of understand that, but it was very surprising when I first saw it. So it's the antiferromagnetic fuzzy sphere that has the same universality class as the sigma model. Okay. All right, so that's a success, but it was pure
Yeah, I
luck.
was just going to ask, your model looks a lot like Heisenberg model, right? Like antiferromagnetic Heisenberg.
Yeah, let me tell you exactly what the difference is, maybe that will help.
Mm-hmm.
So my wave function in every site is four-dimensional. So I can use this basis here, where those are unit vectors, okay? So this tensor product here is a matrix that has a 1 in only one spot, one entry in the matrix, okay? When I multiply by those sigmas, they multiply only on the left of the wave function. So they leave this other part of the Hilbert space untouched. So if you think of the Hilbert space of my theory as a tensor product of two, this part, the nearest neighbor interaction, only acts on the first one, acts on the first qubit, and the second qubit is left unchanged. So if my Hamiltonian was just the nearest neighbor interaction, that means that my Hamiltonian would be a product of a Heisenberg model, or to be precise, a spin-half antiferromagnetic Heisenberg chain, tensor product with something that doesn't have a Hamiltonian. The Hamiltonian is 1. All right? So that's the relation between my model and the Heisenberg model. Now, the Heisenberg model, you cannot tune criticality on it. The only coupling here is an overall constant, right? So that's where the kinetic term that's not in the Heisenberg model appears. The kinetic term involves a commutator, so involves multiplications from the left and from the right. So they act on both qubits at every site. Therefore, it's no longer true that the eigenstates of the fuzzy model are just a tensor product of the eigenstate of the Heisenberg model times anything. Okay. So
I think Heisenberg, antiferromagnetic Heisenberg is critical by itself, right? You don't need to tune anything. You just
go
to a large number of sites and will be.
Yeah, but it is not
plus,
the sigma model. That's what I'm trying to argue here. It agrees the sigma model only in the deep infrared, but not in the region that I call ultraviolet.
But it should not agree with sigma model. Sigma model is gapped, right? And Heisenberg model is gapless.
It depends what you mean by gapped. You want a theory that's in the same universality class as the sigma model. So you're going to get a gap that's tiny in cutoff scales.
Yeah, but it's still, that's like QCD. That's like saying that QCD is a gapless theory. I mean, there is dimensional transmutation.
It's exactly the same situation. So if I want to describe QCD, not only to get hadron masses, but to get deep inelastic scattering correct, I have to match the infrared and that region that I call ultraviolet, not at the cutoff scale. Okay. What I'm arguing here is that, so this for the others, right? So the Heisenberg model, that part is well known. It's a gapless theory and has a dispersion relation that's linear in momentum. So it's kind of a relativistic, right? So what I think is going to happen is that the ground state of the theory that has only the nearest neighbor is going to be made of the Heisenberg ground state times anything. So it's exponentially degenerate in the volume because you have an arbitrary two-dimensional vector at every site. The kinetic term is going to lift this degeneracy. But it's very small for a small g compared to the other term. So the terms, the states that are excited states of the Heisenberg model times anything, they decouple from the theory. And the states that survive, if we include only the nearest neighbor part, you still have a lot of those states. And that's why you end up with a sigma model that still has a large number of states. They don't come from the excited states of the Heisenberg model. They come all from the ground state of the Heisenberg model. Right? I have little evidence of that because what I would like to do is to solve this theory in perturbation theory. By solving, I'm not going to find the spectrum, of course, but I should at least be able to calculate the beta function at small g and prove indeed that the beta function does what I want to do, right? I was not able to do that It's a very degenerate perturbation theory, and it's a little embarrassing, but I cannot do it, okay? But I can set up the perturbation theory and see, for example, that the gap as a function of G squared should go with 6 powers of G. That's because first order perturbation theory vanishes because of some obvious symmetries, and then you're left to the next order, okay? So if I use this in a small box, perturbation theory is good and should give me splitting that's of order G6. And that's exactly what you see diagonalizing on the lattice, okay, with great precision. It's completely different from other truncations, by the way, where approaching G equal to 0 doesn't give you, it's not critical, right? Anyway, so that's the picture I have, right? The Heisenberg model. So if you think in terms of the lattice and you measure things in lattice units, we are looking for a critical theory if you're trying to reproduce the sigma model. Sigma model has a finite gap in physical units, but the gap approaches 0 in lattice units. And so I need a theory that reproduces that part. And the Heisenberg model is not going to do this from, by itself. It's this term here, or there are many others. I mean, there's a whole universality class, right? That lifts the degeneracy of the ground state and then allows me to have the whole Hilbert space of the sigma model. I understand that this part of the argument is cheap talk, right? I would like to have an actual calculation and figure out how to do perturbation theory in G squared. And it should be possible because the leading order is the Heisenberg model at solvable. So it seems to be a technicality, but anyway, I don't have it at this point, all right? So finally, we get to gauge theories. And after all this preparation, it's kind of obvious what's to be done and not to be done here, right? So the usual formulation would be to put the theory on a spatial lattice. The wave function is a function of the different links. And every link now is not a vector, but it's a SU2 matrix, right? Gauge transformations like this. There is a transformation on the left of the link, and a transformation on the right of the link. And of course, a gauge transformation that's left on one link is going to be on the right of another link. But that's always standard stuff. There's an operator that gives you the link operators, right? That just is like a position operator. And there are operators that implement the gauge rotations on the left and on the right. They obey the usual relations that are, they generate 2 SU2s, one on the left, one on the right. They transform U's as they should. And the different position operators, different link operators, they commute even if they're on the same link. Okay. So this is a standard Kogut-Susskind formulation of gauge theory on a spatial lattice. Okay. The Hamiltonian has a similar formula from what we had before. The only difference that instead of nearest neighbors, we have plaquette terms. And the novelty is that we demand gauge invariance of all states. And that's the same as demanded that at every point, the amount of charge that comes in and the charge that goes out vanishes for physical states. So there's a constraint, if you want. This formulation, of course, is completely equivalent to the standard one that people in my generation learn with the path integral of the F mu, right? And the connection is just that you take this Hamiltonian, you write a path integral for the partition function. You have the implementation of the Gauss law amounts to adding a Lagrange multiplier that plays the role of A0. This is just a standard Kogut-Susskind formulation, and you get a Hilbert space that, again, is infinite dimensional at every link. One strategy to make it finite dimensional is to substitute SU3 by a set of points. Again, you'd like the set of points not to lie on the equator, but to be kind of fairly distributed over the manifold. And there's a finite number of ways of doing this. You can look up in a book. Here's a node calculation of the early days of lattice QCD, where you see the result. That's the plaquette as a function of the inverse coupling. And what you see is that there's a sharp first order transition instead of a smooth approach to continuum. And more than that, you get one result when you increase G, another result when you decrease. So there's a hysteresis, and that's a hallmark of first order transitions. Again, it's the same argument. When G squared is very small and there are no configurations with arbitrarily small action, the system freezes and doesn't have a continuum limit. Still, just for the heck of it, I decided to see how much I could push this. So I took the largest discrete subgroup of SU3 that's kind of well distributed over SU3 in a particular sense. Turns out to be this group here with 1,080 elements. A little bit of a problem already, because the Hilbert space in every link is going to require 11 qubits. This is finite, but really, since the cost of the time evolution is going to be exponential on that, it's not good news. But we try to use an improved action that has not only the plaquette term, but a plaquette square term, and tune G0 and G1 in such a way that we get as close as we can to the continuum limit. And what we find is that first we can. Eventually, there is a first order transition. So this theory does not have a continuum limit, just like the Platonic solids for the O3 model. What you can do is the following. So here is the mass of a particular glue ball in some units and the light spacing. As you approach the continuum and you move to the left and you use regular SU3, you approach what's probably the correct answer. That's this number here. And this is right because we did the calculation, just for the heck of it. Then you can do the same thing with a theory that has a 1080 discrete subgroup. And it looks like it's going to approach the same point, except that you can go beyond this value of A. You cannot make the correlation length arbitrarily large. So you cannot extrapolate all the way to 0. So there is an uncontrolled approximation here. So maybe this is going to be good at some point in history when you can do those calculations and nothing else. And this is going to be precision enough. But it's not it's not a controlled calculation and never will be. So cross that. What about the momentum space truncation? Right? Instead of spherical harmonics on SU3, I could use spherical harmonics spherical harmonics on the sphere, use spherical harmonics or like Wigner G functions in SU3. Preparing this talk, I realized that there is no clear evidence that this fails, but my experience in the Sigma model suggests that it does. So I don't have anything intelligent to say, but it's not going to work. For me, it's pretty clear it's not going to work. Can I do some kind of fuzzy truncation, though, of gauge theories? Well, for SU2, claim you can, and it's not even that difficult. The point is that a link transforms under gauge transformation from the left and from the right. So basically, you have to set up a theory that has an SU2 cross SU2 transformation in every link. But SU2 is the Lorentz group, so we're all familiar with the representation theory of that group. So the bottom line is this. You're going to take your link operator. It's a 2x2 matrix because it's an SU2 matrix. But every entry now is not a number. It's going to be an operator. And this operator is going to be a 4x4 matrix. And it's written here what it is. The condition for unitarity of this SU2 matrix, after all, is an SU2 element, right, is mapping to this condition on these big gammas. And of course, this is satisfied by this construction. So this is all very similar to the fuzzy sphere construction. Right? From that, you can see how this use would transform under gauge symmetries and infinitesimal generators. Again, just like the O3 fuzzy model, amount to be commutators with Pauli matrices, essentially, on the left and on the right. So again, it's as if I was doing a field theory, an SU2 gauge theory, where every entry of the SU2 matrix were non-commuting numbers, or if you prefer, operators. The point is that at the end, I end up with a wave function that's a 4x4 matrix, at least in every link, right? So it's a 16-dimensional Hilbert space for every link, as it was 4-dimensional 2x2 matrix for the fuzzy sphere. The parts of the algebra that matter to us, the fact that there is two SU2s that commute with each other, and they transform the field operators as Kogutsu's kind told me to, they are still valid for this other operators that I have here. The only thing that's not is that the different components of the link on the same site no longer commute because they are some matrices that don't commute. So that's exactly like the sigma model. The Hamiltonian reads identical to the Kolbe-Susskind Hamiltonian, except that now those things have a different meaning. They are finite dimensional operators in every link. In fact, they are 16 by 16 matrices, right? And the same thing for the Gauss law. It's again a constraint that's finite dimensional. Okay? So you end up with a 16-dimensional Hilbert space in every link, so it can be described by 4 qubits. We actually worked out what a good way of implementing the time evolution given by the kinetic term and the plaquette term. If you care, involves like 200 C0 gates. People tend to count C0 gates because they are noisy, and they are the ones that currently give the most trouble. This number, if we increase the number of qubits, this number 200 goes quickly to the hundreds of thousands. So that's why keeping down to 4 is really good. It has exact gauge invariance. So it has a fighting chance of actually corresponding to the continuum gauge theory. The question is, how do we prove it is? And the answer is we don't. Because again, Monte Carlo has a really bad sign problem. So I cannot simulate this theory and get results, numerical results like I did for the sigma model. Tensor networks are just not good in 3 dimensions. It's a long story, long, complicated story with a lot of qualifiers, but it's not going to work. Okay. To make it worse, I said that in leading order in small g, the sigma model was basically the Heisenberg model, tensor, some trivial thing. Here, the separation happens. You get a theory that has only the plaquette term times anything in leading order in G. This anything has appeared in the literature already. So it has a name, and I should have the citation here for Orland and Norlick. But this model is not understood. It's not solvable. We don't know if it's gapless, if it's not gapless, what the dispersion relation is. We know nothing. So
is there an analog here of making it anti-ferromagnetic like before by changing the sign of the bit, or?
Yeah, you can define this as a plus or a minus sign. And a good question is, which one is the right one? I don't know. I don't know if any sign is the right one. Okay. I just think that because of my experience in the sigma model, this has some of the characteristics that I need. For example, the fact that the ground state of this theory at small g is going to be given by the ground state of Orland-Harlick, times any, and then the kinetic term, the electric term, right, is going to split this degeneracy and give me a correction that we can count. In that case, I think because of gauge invariance, it goes to the G to the 16 or so. Okay, so I can set up a perturbation theory in small volumes, and it does what's supposed to do. Okay, anyway, perturbation theory applies in a small volume, and even though I cannot calculate the number because I don't know how to solve the leading order, it has the correct powers of G. Also, you can see that if you do the same approach for a large volume, the same perturbation theory would have infrared divergences, what suggests that, yeah, it's because the theory cured these infrared divergences because it confines, and my calculation doesn't contain that ingredient. But here's the result, numerical result for the case of one single plaquette. Okay, the other truncations, of course, are not gapless, while our truncation by construction is gapless, right? Because at 0G, it has a bunch of states that are degenerate. This is not 0 all the way. Here I have in a log scale, and then you can extract the correct power of G square. And it's an integer power of G square, as you expect from regular perturbation theory. Okay, so that's the analog of the previous graph that I had in the sigma model. But it's pretty much an open problem, okay? The open problem being, I don't understand this model at all. I'd like to understand this model as well as understand the Heisenberg model. Or to be sincere, even knowing that, it's not obvious how to do the highly degenerate perturbation theory one has to do to compute the beta function. Okay? I suspect all those problems are those completely solvable, and I'm just being stupid. It's perturbation theory after all, right? One should be able to do that. Anyway, I'm going beyond my time, so I just want to flash here the take-home lessons that we learned from this exercise. And if you guys have any questions, we can talk further. Thank you.
Thank you, Paulo. So I have a quick question. I'll abuse the position I'm in. So you mentioned that checking this with tensor networks is going to be hard because your target is 3D. It's 3 spatial dimensions. But you could use tensor networks in 1 dimension and check what happens.
Yeah, we talked a little bit about this over email. So Turing mills in 1+1 dimension, as we discussed, it's the trivial theory, has only 1 degree of freedom. That's the Wilson loop on the periodic boundary condition.
But you have to get that much right. It's trivial, but that's a good thing. You know the answer.
Yes.
So if you don't get it right, it's very bad. So you have to check.
Yes and no. So let me put it that way. So let me tell you one thing I don't know how to do. Okay, I don't know how to do the Polyakov loop. Okay, the loop on the time direction, because in the Hamiltonian language there is no such a thing. Okay, that makes me believe that this whole popular arguments people make with Polyakov loop are actually not kosher, but that's a separate discussion. Okay, so I'm trying to defend my theory fails there. I'm not going to worry because I don't think that's real anyway. Now the Wilson loop on the space direction, that's real, and you're right. I would like to get that right. What I think is that this is more or less orthogonal. Getting this right is more or less orthogonal to getting the dynamics correct to get the right continuum limit. Of course, I want both to work, right?
I agree.
We should think about it, okay?
Right, but, yes, I completely agree. I just think that, they are orthogonal, but I think getting both right is kind of important, and one of them is easier to get right than the other, and so it's a natural starting point. But anyway, yeah.
Yes, we should think about it.
Yes.
I agree with you. I agree with you. But I'm trying to drum up interest on doing this. Okay. Right. It's a very interesting model in itself. It's fairly simple. It's one of those models that you can explain to your grandmother, and it's like the Ising model. It's slightly more complicated. And I looked, and nobody knows anything about it.
I think Marco has a question. So, Marco, go ahead, please.
Thanks. Very nice talk. It was actually 2 questions. One is, I kind of remember that there is an obstruction to using this fuzzy construction for SUN groups, in the sense that if you look at if you consider all of the commutators with this truncation that you are using, you actually always tend to generate UN instead. Perhaps this is not so much of a problem, but I was wondering if somehow this is avoided here. And the other question that I have is, in the case when one uses this fuzzy construction to regularize the space-time instead of the target space, you have this phenomenon of UVIR mixing. I was wondering if there is something analogous to this effect when you use the fuzzy construction to regularize instead the space of the target space, basically.
Yeah. So the first question, the extra U1, I think this applies to SU3 and above. I think SU2 is kind of a special case. I have to confess, I've read people talking about those things and I don't really get it. It's usually in the language of these quantum link models that are different from what I'm saying here, fundamentally different. There are a bunch of other things that I had to rush over. For example, this choice of the kinetic term here seems the natural one to me, but it's clearly not unique. And some of those have an extra U1, some of them break that U1. I will refer you to our paper, or those things are discussed to some extent, okay? Regarding the UV infrared mixing, I'm sure it's there. but it's in field space, so it's not a problem. It doesn't impact, RG, arguments. Anyway, I think it's a feature, not a bug in that circumstance. All right. And again, that's all. I have nothing more, smarter to say than just this. Okay. Listen, maybe I was not clear enough. I tried to organize this in a logical way, and it's a lie. Okay. For me, the fuzzy sphere regularization was a natural thing to do, so I did it. Then I wanted to prove that was right. I did some numerics, and then I realized there are a bunch of other simpler things one could do. And then I tried to do them. They fail. So it's not that I had a big insight. So I have no idea, for example, if no commutative geometry is at the heart of those things working. Maybe it's not. Maybe it's some other feature. And I'm trying to identify exactly what is the feature that matters. I think this duplication of the Hilbert space, to have a Hilbert space that kind of has the square of the number of dimensions of the naive thing. So take the Heisenberg model and multiply it by something trivial and then perturbing. I think that's essential to get a continuum limit that's under control, but I don't really know. Yeah. I should say also that of course, we did look into generalizing this to SUN, and even taking larger representations of SU2. And what happens is that the only thing that fails, that doesn't go through, is that there is no analog of this equation here, of the unitarity condition. Now, if I want to interpret my thing as a non-commutative geometry construction, I want something like this. But do I need that? I don't know. The Sigma model had it, and it worked. But maybe it was a fluke. It was an accident. In which case, I know how to do SUN, because Roland Orlik did it for me. Okay? And I can do SU2 with other representations too. Sorry, I went on a tangent a little bit.
Does anybody have other unasked questions?
Can I ask a quick one? Oh,
Yeah,
sorry.
please.
So Paulo, in the sigma model example, if you chose j equals 1 and not j equals 1/2, is the story the same?
That's a very good question. So I assume it would, and it would actually approach the continuum faster. But I actually think it does not now. And let me tell you why. There you go. Okay. So I give you sort of a hand-waving explanation why you get criticality in this model. And it relies on the fact that the spin half Heisenberg chain was gapless. It turns out that for spin 1, the Heisenberg chain is not gapless. It's gapped.
I see. So the whole mixing thing doesn't happen.
So yeah, on the other hand, for 3 halves, I think it should work. Okay, so there is a test of this picture that I'm trying to push here, and it's running on the computers right now. Hopefully, we're going to do spin 1. It's not going to work. We're going to do spin 3 halves. It will work again.
Gotcha.
Anybody cares, but it's going to answer a big question for me.
Okay, I see.
Beautiful.
Interesting.
Okay. Well, if there are no further burning questions, Paulo, thank you so much for this talk.
All right.
It was
Thank you.
really,
Thank you for having me.
fantastic. Yeah.
Mhm.
All right.
Thank you.
Thanks again.
And yeah, Alex, we should work that out and figure it out.
Yeah,
Okay.
we should connect. Yeah. Okay.
Bye.
All right.
Nice to see you guys.
Nice
Thank
to
you.
see you. Yeah. Bye-bye.